You write a single NumPy line, and 1,000 things happen at once. No loop, no if statement, no visible control flow. And somehow it works. Then you change the shape of an array, and the code that used to be fast becomes slow. Or worse, it still runs, but gives you the results that you didn't expect it before. No error, no warning, just different behavior. This is the moment where many people think NumPy is weird. It's inconsistent or badly designed. It's actually not. NumPy feels unPythonic because it is solving a completely different problem than Python was designed to solve. In this video, we will see exactly which Python rules NumPy breaks, why it breaks them on purpose, and how all this connects directly to memory and of course hardware. Once you see that, NumPy stops feeling strange and starts feeling precise. Python is built around a very specific mental model. You work with objects, you manipulate them step by step, use loops and conditionals to describe how programs should move forward in time. That model is intuitive, it's readable, and it's great for general purpose programming. NumPy doesn't use that model. NumPy is built around the data flow. You describe what should happen to large regions of data, and NumPy applies those transformations all at once. There is no visible step-by-step execution because the steps do not live in Python anymore. This is the first major point of friction. Let's look at a simple example. Two arrays, same shape, element-wise addition, no surprises, and now change only one thing. There is no loop, there is no explicit replication, and yet the operation still works. For many Python programmers, this feels like magic, or worse, like NumPy is guessing what you meant. What is actually happening is much more mechanical. This is broadcasting. Broadcasting is a rule system for aligning shapes so that memory can be processed in bulk. NumPy looks at the shapes of the inputs and asks a simple question. Can these arrays be interpreted in a way that lets their element line up in memory during computation? If the answer is yes, the operation proceeds. If not, NumPy refuses. Notice what NumPy does not ask. It doesn't ask what loop you would have written. It doesn't ask how you would have implemented this in Python. Logic lives in shape, not in control flow. This is why NumPy code often has very few loops. Loops are not forbidden. They are just wrong abstraction from the kind of work NumPy is optimized to do. The next place where NumPy feels unPythonic is error handling. In pure Python, errors tend to be immediate and local. If you divide by 0, Python stops right there and tells you something went wrong. Now look at this. No exception, no crash, just a special value. This just feels wrong to Python users. It feels unsafe, but this behavior is not coming from NumPy being careless. It's coming from NumPy choosing to expose how the hardware actually works. Floating point units on CPUs do not stop execution when something unusual happens. They produce special values and keep going. That behavior is fast and predictable, which is exactly what numerical computing needs. NumPy mirrors that behavior instead of wrapping everything in Python exceptions. This design choice makes NumPy faster and more composable. It means that mistakes can propagate silently if you are not paying attention. That trade-off is intentional. Another source of confusion is when errors appear late or far away from where the mistake was made. Consider this. This looks like two operations. In practice, NumPy treats this as a bulk transformation over memory. You are not watching elements flow through Python line by line. You are defining a computation that will be applied to an entire array. This is why debugging NumPy sometimes feels harder. The computation doesn't live at the Python level anymore. It lives in compile code that runs over the memory. NumPy is explicit about what happens to data, not about how control flows through the program. This difference becomes even more important when mutation enters into the picture. From a Python perspective, this feels dangerous. You modified B, but A changed too. From memory perspective, this is unavoidable. Both arrays describe the same block of memory. There is no copy, there is no isolation. NumPy consistently chooses exposure over protection. It assumes that if you care about performance, you are willing to reason about memory. That assumption is why NumPy sometimes feels weird. It is also why it scales. Broadcasting feels strange because logic moved from loops into shapes. Error handling feels strange because NumPy mirrors hardware behavior. Mutation feels dangerous because memory is shared instead of copied. Debugging feels different because execution happens in bulk, not step by step. All these behaviors come from the same design decision. NumPy optimizes for memory and hardware, not for Python semantics. Once you stop expecting NumPy to behave like Python, its design becomes consistent, even predictable. This is the change in perspective that matters. NumPy is not a better way to write Python code. It is the way to describe computations that maps cleanly onto hardware. Python is just the language used to describe them, and that brings us to the final step. If NumPy is so tightly aligned with memory, then the last question is obvious. How exactly does it exploit the CPU itself? Why do contiguous arrays matter so much? Why do caches and vector units change performance so dramatically? That is what we will discuss next. If you have any questions or any important points relevant to your experience using NumPy, please feel free to share it in the comment down below. Don't forget to subscribe to the channel to not miss the next video. And as always, good morning, good afternoon, and good evening. Bye.